Today we're going to look at section 3.5, which is called rational functions and their graphs. So today we're going to specifically focus on finding domain of rational functions and identifying vertical asymptotes. We've talked about rational functions in the past, but let's kind of get the definition again. A rational function are quotients of polynomial functions. Remember, quotient means division. So this means that the rational function can be expressed as the following. F of x equals p of x divided by q of x. P and q are polynomial functions, and in order to then be a rational function here, q of x cannot equal 0. Okay, remember, we never want our denominator to equal 0 because if we do, then we have something that is undefined. So we have to make sure that that won't equal 0. Okay, so rational functions, once again, if it's a polynomial function, that means that there are some variables involved. So rational functions have variables in the denominator of a fraction. All right, we've also discussed domain in the past, but we're going to practice more with that today. So domain of rational functions. The domain of a rational function is the set of all real numbers except the x values that make the denominator 0. Okay, so like I mentioned before, we never want to divide by 0 because then it turns into something that is undefined. So we never want our denominator 0. Any value that does make the denominator 0 cannot be a part of our domain. So let's take a look at some examples. We are going to find the domain of each rational function. So our first problem, we have f of x equals x squared minus 25 all over x minus 5. So once again, in order for us to state the domain, we need to focus on the denominator. So in this case, x minus 5 is my denominator. I have to set that equal to 0, solve for x. That's the value that cannot be in my domain. So all I would have to do here is add 5 to both sides. So that means x equals 5 would turn my denominator 0, which means I do not want x to equal 5. If I plug any other number into that denominator, we will not get 0. So 5 is the only number that's excluded. So we're going to write our domain in interval notation. So remember, we go from left to right, so from negative numbers up to positive numbers. We can have any negative value, so we can start from negative infinity and go up until we reach 5. But remember, I do not want to include 5, so we have to have a parenthesis. But then I can keep going on the other side of 5. So on the right side of 5, we can keep going up towards positive infinity. So here is my domain. Essentially, it's all real numbers except for 5. If we take a look at the next problem, g of x equals x divided by x squared minus 25. Once again, to state our domain, we're looking at our denominator, x squared minus 25. There's several ways here when I set that equal to 0 that I can solve. It is a quadratic, so we could factor if possible, which this one is because this is a difference of 2 squares. So I could know that this is x plus 5 times x minus 5. And then I would have to set each of those equal to 0 to continue solving for x. So that means I would have to subtract 5 over here, add 5 over here. So that tells me that I have two values that cannot be included, negative 5 and positive 5. Technically, the other way we could have solved this was because there is no x value, we could just move that 25 over to the other side, and we could do the square root method. Notice that I could take the square root of both sides. Square root of 25 will give me both a positive and a negative 5. So this time we have two numbers that cannot be in our domain. So once again, we're going to write our answer in interval notation. We're going to start with negative numbers. So I can go from negative infinity until we reach negative 5, but it's not included, so we need to have a parenthesis. On the right side of negative 5, I can go up until I reach positive 5, but it cannot include it, so I need another parenthesis. And then on the right side of 5, we can go up towards positive infinity. So here is my domain. There were 2 restrictions, so notice there are 2 different union symbols that help us bring all of that together. If I take a look at this third problem, h of x equals x plus 5 divided by x squared plus 25. So once again, I'm looking at my denominator and I'm asking myself, what is going to make my denominator 0? Well, notice that this time, because it's x squared plus 25, I'm not going to be able to factor because this is not a difference of 2 squares. That means I would have to subtract the 25. So then x squared equals negative 25. Notice that when I take a square root, I have a negative. So that means that we're dealing with imaginary numbers. Okay, when we're talking about domain, we're talking about real numbers. So in this case, if the only restriction is that I can't put some imaginary numbers into my denominator, that means that all real numbers can go into that denominator and it will never turn it to 0. So because I don't have a restriction, then I know that I can have negative infinity up to positive infinity. So once again, if my only restriction turns out to be imaginary numbers, then we are good to go with all real numbers. All right, I suggest that you pause the video and try these 2 checkpoint problems to find the domain. Hopefully we noticed that in the first example, negative 1 is getting excluded from the domain. And in problem number 2, there would only be imaginary numbers that get excluded, which means that I can have all real numbers, so negative infinity to positive infinity. All right, let's start talking about vertical asymptotes. Okay, it says what value of x will not be in the domain of our rational function f of x equals x squared minus 3x minus 4 all over 4x minus 8. So like we just reviewed, it's my denominator that I need to focus on if I'm trying to figure out domain. I'm going to set my denominator equal to 0, solve for x, which means we're adding 8, and dividing by 4. So notice that means my restriction. The only value that wouldn't work is 2. Okay, so this whole section is going to be that we're going to be graphing. So what does that mean? If there's a restriction in my domain, I can never have 2 be a part of my graph for x. So how would that look? Well, let me erase this work right here. Since it was not included in the domain, we must draw a vertical line at x equal 2. This becomes what we call a vertical asymptote of the graph. So notice that this would be the layout of our graph. So notice that we have this vertical line at x equals 2. And so notice that there is something on the left and the right-hand side of it. And on either side, it's getting closer and closer and closer to that vertical line, but it's not ever going to touch or cross through it because once again, 2 can never be an x value on my graph. So locating vertical asymptotes. If f of x equals p of x over q of x, and that's a rational function in which p of x and q of x have no common factors. That is the key here. No common factors. Okay, meaning I can't have the same thing in both the numerator and the denominator. So it needs to be as simplified as possible. That's why we practice simplifying rational expressions before we left for winter break. A is a 0 of q of x. And then if that's the case, then x equals a is a vertical asymptote. Okay, so if a is a 0 of q of x, then x equals a is a vertical asymptote. So that's kind of what we just talked about in the previous slide. Remember, 2 was excluded, so x equals 2 was my vertical asymptote. All right, so let's find vertical asymptotes, if any, of the graph of each of the following rational functions. So we've got f of x equals x over x squared minus 1. Once again, in order for us to identify vertical asymptotes, we have to make sure that our function is as simplified as possible. And so in order to simplify rational expressions, we have to make sure everything is as factored as possible. The numerator is just a monomial. We can't factor monomials, but my denominator is something that can definitely be factored. X squared minus 1 is going to be the same thing then as x plus 1 times x minus 1. Okay, once everything is factored, notice that there's nothing in the numerator that is the same as the denominator, because the denominator is made up of two different binomials, which is different than a single monomial. So I can't simplify that down any further, which means that now I can identify the vertical asymptotes, and they're going to be whatever numbers make my denominator 0. So in this case, there happens to be two different scenarios here. So if x plus 1 equals 0, that means that I'd have to subtract 1. So a vertical asymptote here is going to be that x equals negative 1. So on my graph, I would have to draw a vertical line at negative 1. Then over here, x minus 1 equals 0, I would have to add 1. So that means that a second vertical asymptote is x equals positive 1. So there were two vertical asymptotes because we had two different values that would make my denominator 0. But notice every single time I named my vertical asymptote, I wrote it as an equation. It's x equals a number because it needs to be represented as a vertical line. Let's take a look at the next example. H of x equals x minus 1 all over x squared plus 1. Once again, I want to try to simplify this as much as possible. So if I am factoring, I can't factor the top, so I'm going to leave it like that. Notice that x squared plus 1, because that 1 is positive, I can't find numbers that add to or that multiply to positive 1 but technically add to 0. So that means that that doesn't change either. So even though we tried, this one is not factorable. So that means that we can't simplify it any further. If I then focus on setting my denominator equal to 0, notice that the very first thing I'd have to do is subtract 1. So then if x squared equals negative 1, I would have to take the square root. And once again, here I have a negative number under a square root, making us have imaginary numbers. So that means that there is no value that would turn my denominator to 0. And so because there is no restriction on my domain, that means that there aren't going to be any vertical asymptotes. So I would say no vertical asymptotes. In this last one, g of x equals x minus 1 all over x squared minus 1. So if I look at the numerator, I'm not going to be able to factor that. So that's just going to stay x minus 1. X squared minus 1 would be factored into x minus 1 times x plus 1. So notice this time I do have something in the numerator that's also in the denominator. So we get to simplify that. And so really, I want to focus on 1 over x plus 1 to determine my vertical asymptotes. So because there's only one denominator, that means there's only one equation that I have to set equal to 0. So then I'd have to subtract 1, which means that my vertical asymptote is at x equals negative 1. All right, so let's identify the vertical asymptotes of this function. We've got f of x equals x cubed minus 2x squared minus 8x all over negative 2x squared plus 4x. So once again, in order to identify vertical asymptotes, we have to have everything as simplified as possible. So let's see if we can factor. The numerator definitely has a GCF of x, so I'm going to factor out an x, which would leave me with x squared minus 2x minus 8. In my denominator, I also have a GCF. I'm going to take out a negative 2x, which would leave me then with an x, minus 2. My numerator, I'm going to continue to factor because notice that I can find two numbers that multiply to -8 but add to -2. That's going to be -4 and +2. So now that everything is as factored as possible, notice that there is something that can simplify. There is an x both in the numerator as well as the denominator. So that's going to simplify down. And so now we're just left with x minus 4 over x plus 2 on the top, and then -2 times x minus 2 on the bottom. So now that I have that out of the way, I can focus on the denominator. Any factor that contains an x, so in this case, just the x minus 2, I would set that equal to 0, which means I have to add 2. So I do have a vertical asymptote. It is going to be at x equals 2. But just like the other example, that third example, when something is going to be able to simplify down, originally we did have a restriction where if I didn't simplify, I would have seen that, hey, there's an x, so then x equals 0 would have potentially been a vertical asymptote. But because I simplified that down, that no longer became a vertical asymptote. But something still happens at this case at 0. Or in the last example here, something still happens to that 1. So what would happen is that it would actually create something that we call a hole. So notice that here's my graph for this particular function. So I do have my vertical asymptote at x equals 2, but notice here at 0 for x, there is a hole, meaning that my graph is not actually going to have a value at 0. Okay, so that's what happens when we are able to simplify down rational expressions. When we then technically would graph them, if we don't have a vertical asymptote there because we simplified it down, we still have a restriction where it can't be in our domain. It creates what we call a hole. So just for your knowledge. All right, so go ahead and try these two checkpoint problems where I want you to find the vertical asymptotes, if any, of these graphs of the rational functions. Okay, so hopefully you noticed that in the first one, I couldn't simplify that down. X squared plus 64 is not going to have any restrictions, which means there are no vertical asymptotes. But in the next one, I could factor that denominator, which reduced down my rational function to 1 over x minus 8. So then when I set that denominator equal to 0, my vertical asymptote is x equals 8. And then notice that because this got taken out, if I was to have set that x plus 8 equal to 0, it would have been -8. So that means on my graph, I would have a hole when x was at -8. Okay, but that's what I wanted to cover today. So we can find domain of our rational functions and we can identify vertical asymptotes. Now, I do want to point out really quick that with domain, you don't want to simplify your rational expression. So you want to just look at the entire denominator to determine what is going to be excluded. It's just with vertical asymptotes that you need to simplify your rational functions.